Welcome, university students. Think of this explainer as your ultimate academic roadmap. You're probably tuning in because you're ready to make that massive leap, going from just consuming the knowledge in your textbooks to actually creating it. We're going to demystify the whole scientific research process, from that first light bulb moment all the way to a published paper. It takes planning, sure, and a ton of integrity, but by the end of our time together today, you're going to have the exact blueprint to make it happen. Okay, let's look at our syllabus. We've got 6 core phases to tackle. First, igniting the idea. Then, the literature review, building the foundation, design and ethics, writing in APA style, and finally, passing peer review. Let's not waste any time, right? Let's jump straight into Phase 1.
Section 1. Igniting the idea. Every single great study out there, seriously, no matter how complex it seems, fundamentally starts by just noticing a problem or a weird pattern in everyday life. It could be something as simple as observing a peculiar behavior in a waiting room, or maybe picking up on a hidden, unanswered question in someone's life story.
But here's the thing. While your personal curiosity is the perfect starting line, that alone isn't enough for a full-blown research paper. Your idea has to pass 2 big tests to be viable. First, it has to be interesting to the broader scientific community. And second, it must be highly novel. Basically, you can't just repeat known facts. You're looking for the gap, that missing puzzle piece in our current understanding. You've got to bring something truly original to the academic conversation.
Section 2. The literature review. Once you've got that spark, it's time to map the territory. This is where you dive headfirst into specialized academic databases. Think PubMed, PsycInfo, or JSTOR to see exactly what's already out there. Trust me, you do not want to spend months reinventing the wheel.
Now, when you're looking at primary sources, which, by the way, are the original reports written by the actual scientists who did the work, you really want to use the 3 C's framework. You've got to be comprehensive, meaning you're checking multiple databases. You need to be critical. Don't be afraid to openly challenge the methods those previous researchers used. And finally, you must be clever. Actively hunt for the flaws, the anomalies, or the limitations in their work. Actually finding those flaws, that is exactly how you pinpoint the specific unanswered question your research is going to tackle.
Section 3. Building the foundation. So after narrowing your focus, you have to build a concrete foundation. You're taking that overarching idea of yours and translating it into a testable hypothesis. Basically, a super specific prediction of exactly what you expect to observe. Science deals in tangibles, right? And that is exactly why operational definitions are an absolute game changer. You can't just measure a vague, abstract concept like happiness or hunger without defining them first. You have to explicitly state how a variable will be measured. For example, if you're studying hunger, your operational definition might be 12 hours of food deprivation. Bam! Concrete. Doing this ensures your research doesn't just fall apart, because any other scientist out there knows exactly what you mean and can replicate your work.
Along with defining your terms, you've got to clearly differentiate your variables. First up is your independent variable, or IV. This is the factor you are directly manipulating. It's the presumed cause. Next is the dependent variable, the DV. That's your measured response, the presumed effect. And finally, you might run into a quasi-independent variable. That's a pre-existing characteristic, like age or gender, that you can't exactly randomly assign, but you still use it to group people. Getting these straight, it's literally the bedrock of your study.
Section 4. Design and ethics. With your variables locked in, we move to the architectural blueprint of your study, your research design. This is how you plan to gather accurate info safely, responsibly, and logically.
Now, based on what we can actually control, there's a huge difference in how we design studies. If you want to absolutely prove that your independent variable caused the change in your dependent variable, you use an experimental design. The absolute magic key here is random assignment. It ensures all your groups are perfectly equivalent before you even start. But sometimes random assignment is impossible or, frankly, unethical. You can't randomly assign a medical diagnosis to a participant. In those cases, you use a quasi-experiment, where you're simply comparing people who already have those pre-existing characteristics.
But listen to me carefully on this next point. Before you collect a single piece of data, your compass must point to ethics. It is entirely non-negotiable. You absolutely have to get approval from an institutional review board, an IRB, and follow the Belmont Report guidelines. First, you show respect for persons through informed consent and voluntary participation. Second, beneficence, maximizing the benefits while minimizing any risks. And third, justice. You have to ensure a fair, equitable selection of your participants. Because science without ethics, well, that's just not science we want to do.
Section 5. Writing in APA style. Okay, so your data is collected and analyzed.
Now it's time to tell the story. But remember, scientific writing isn't some sweeping creative novel. It is an objective, highly systematic, and totally impersonal report of exactly what happened.
To structure your behavior science paper, I want you to picture an hourglass. You don't just dump all your data on the reader. You start really broad at the top, introducing the general topic. Then the hourglass pinches inward as you narrow down to the exact nitty-gritty specifics of your unique study. And finally, at the bottom, the hourglass broadens back out as you discuss the general real-world implications of your findings. It's a brilliant flow. To pull off that hourglass shape, you need to strictly adhere to the 7 major sections required by APA style. You start with a snappy title page. Keep it under 12 words if you can. Next, an abstract, which is just a tight 150 to 250 word summary of the whole shebang. Then comes your introduction, reviewing the literature and stating your hypotheses. Next is the methods section, written with step-by-step clarity so anyone can replicate it. Then the results. Just objectively report those statistical outcomes, no opinions allowed. The discussion is where you evaluate what those results actually mean for the broader field. And finally, your alphabetical references section. Following this format means any scientist anywhere in the world can easily read and understand your work.
Section 6. Passing Peer Review. The final frontier. You've designed it, ethically conducted it, and formatted it flawlessly. Now you face the final boss in your academic journey, submitting your manuscript to a peer-reviewed journal where blind experts in your field will rigorously evaluate its methodology and importance.
I want you to brace yourself for a second, because rejection rates in top-tier academic journals sit somewhere between 65% and 85%. Yeah, that is incredibly high. But I'm telling you this not to discourage you, but to prepare you. Rejection in science is so incredibly common. It's a completely normal rite of passage, not a defeat. Even the most brilliant scientists in the world see these numbers all the time.
So the real make or break moment is how you handle the feedback. Often you won't get a flat yes or no. Instead, you'll get what's called a revise and resubmit. Do not, I repeat, do not let your ego get bruised here. Actually, you should view a revise and resubmit as a massive win. It's an invitation from top experts to collaborate, refine, and polish your work before it enters the permanent scientific archive. Embrace the critique.
Because once it's published, your findings become immortalized. They enter the permanent scientific record, sitting in a database just waiting to be discovered by future university students during their own literature reviews. Your paper will eventually inspire them to ask entirely new questions, and that continues this incredible, never-ending cycle of scientific discovery. So, as you start looking at the world around you today, looking for that first initial spark of an idea, what will your contribution be?